All right, guys. Today we're going to go ahead and get started with, Chapter 9. And Chapter 9 is difficult, in my opinion, my estimation. It is difficult, but it is also, in my opinion, one of the most fascinating chapters that you cover if you take into account that what we are going to talk about in this chapter happens in our bodies, in every single cell of our bodies, in every single mitochondria of our bodies, every single second of the day, and just keeps us running. And so it's complicated and sometimes difficult to learn, a lot of big words, a lot of complex processes, but when you start to understand it and put two and two together and understand these processes, it's absolutely fascinating. So there's that little reward at the end if you can get past some of the difficult stuff and kind of start to figure it out. Fortunately, it does take a little while to figure out, but we'll hopefully take it a little bit slow, do some activities, and hopefully you get some understanding of what happens and how complex this system is, and have a healthy respect for it. So what is Chapter 9? Chapter 9 discusses the process of cell respiration. So it expands on these ideas that we learned in Chapter 8 with energy transformations and energy transfers, and it gives us an understanding as to how our body takes some kind of raw fuel like sugar and turns it into a usable form of energy. Okay? So cell respiration is oftentimes represented with glucose sugars, okay? And when you guys learned about this in Honors Bio, you probably learned about it using glucose. And this formula down below here in the middle probably looks really, really familiar to you, okay? C6H12O6 is the formula for glucose. We combine it with some oxygen that we breathe in, and our bodies have a really good way of taking those two things, sending through a series of reactions, and at the end getting out CO2, okay, which is what we exhale, and water vapor, which is what we exhale, and getting energy as a result, which is indicated by ATP molecules and heat. Okay, so ATP is just it's a more flexible way of utilizing the energy. It packages up the energy, kind of, if you want to say that, in a little energy packet, and that energy packet can be used to do whatever we might need around our bodies and at the cellular level. And on top of that, we get some residual heat as well. Now, oftentimes this, when we start to get into detail with this chemical reaction, and chances are you've not hit on this chemical reaction in the great detail that we are going to, the best way to understand this chemical reaction is to study where the high energy electrons in this reaction are moving, okay? And I know that seems very abstract and maybe difficult to do, and maybe you've not even covered this in like, AP chemistry or honors chemistry or anything like that, but there's a relatively easy way of doing that. But we've got to do a little bit of review first. If we're going to understand these chemical reactions in terms of how high energy electrons are moving, we have to review what oxidation reduction reactions are, okay? So an oxidation reaction, and this probably is review for you, you've heard it before, they can be relatively difficult. We're going to cover them kind of at a surface level. An oxidation reaction, is where electrons are lost from a compound or an atom. Okay, so we can characterize, in a chemical reaction, we can look at certain compounds or certain molecules or certain atoms, and we can say to ourselves, okay, is that particular compound or atom, is it losing electrons? So if it is, then it's part of an oxidation reaction. Okay. The other half of that is the reduction reaction. Okay, oftentimes these are put together in terms of redox. A lot of people put those two terms together, like Brangelina. They're divorced now, but I don't know who the new power couples are, but they combine those words, oxidation and reduction. They say redox reactions because oftentimes these oxidation and reduction reactions happen simultaneously. There's something that loses electrons in the oxidation portion of the reaction, and then there's something that gains those electrons in the reduction portion. Okay, and there's a really good there's a couple of really good ways of remembering the difference between these two. Okay, so let me pull up here something I can write on so that you guys can have kind of A rule of thumb here, or a really easy way. There's two, I think these are mnemonic devices, right? This is the one I always remember. Leo says gur, okay? Leo says gur, and this describes these kind of reactions. Loss of electrons is oxidation. So if a molecule is losing electrons, it is being oxidized, okay? If a molecule is losing electrons, it is being oxidized. Okay, and the reason this is tricky is because the molecule that gains those electrons is being reduced. And that is not redaced, it is reduced. Reduced would indicate, okay, it's losing something, right? You reduce your weight, you're losing weight. But in this case, they use the term reduced to indicate a molecule that is gaining the electrons that are lost by this molecule, okay? So that's why these redox reactions kind of have to be linked together, okay, where one thing loses electrons, the other thing is going to gain those same electrons. So we have to remember that. Another one you may have heard of is oil rig. Okay? Oxidation is loss. Reduction is gain. Okay? And obviously that's in reference to the electrons. So you can use either one of those, and I always have to do that. I can never just remember oxidation is losing electrons. I only said it that fast because I read it off the screen and made it look like I didn't. Every time I work through these problems in my head, I always say Leo says gur. Loss of electrons is oxidation. It takes an extra second or two, but it gives you the right answer every single time. So I highly recommend remembering these mnemonic devices because they will come in handy, especially when we start to learn this information, okay? So what is happening in a redox reaction, a reduction-oxidation reaction? One substance is going to lose those electrons that we talked about up here, and the other substance is going to gain those electrons. So how can we even identify the electrons in reactions? Okay, specifically these reactions that we're talking about in cell respiration. One of the things that I'm going to kind of give you this like rule of thumb is that you need to follow the hydrogens, okay? And so think about what a hydrogen is, okay? When you look at a neutral atom of hydrogen, okay, a neutral atom of hydrogen has one proton in its nucleus. It has no neutrons, okay? And if it's a neutral atom of hydrogen, it has also got an electron, right? Because a proton is positive and it balances out that electron, okay? So when we look at these chemical reactions in the reactions that we're going to look at in this particular chapter and others that are going to be looked at in biochemistry or organic chemistry, a good rule of thumb, and although there are some exceptions to all the rules, but a good rule of thumb is to look at these compounds and say, do I see hydrogens? If I do, then I also see electrons, because basically a neutral atom of hydrogen, or an atom of hydrogen that's found in a compound, is oftentimes referred to as an electron or assumed to be an electron. And when hydrogens move, electrons are also moving, okay? And so that's going to be something that we will see in the upcoming diagrams, okay? Now, I want you to be aware, because later on, our book uses hydrogens for everything, okay? And one of the things that we're going to see later on in this chapter, and I do not want you to be confused, is that hydrogen oftentimes loses that electron when it's all by itself, when it's not found in a compound. When hydrogen's in solution by itself, hydrogen is oftentimes referred to as H+. So hydrogen can also be referred to as a proton, okay? So think about this, right? Normally, this is a neutral atom of hydrogen, right? If it has lost this electron, which hydrogen likes to do, let's say that goes somewhere else. Let's say it's just gone, and because that happens, what's left? A proton, okay? And that's the reason we see H plus represented often as just looking like this, because all it is a one positively charged proton, okay? So when we look at some of the things in this chapter specifically, we can refer to electrons as hydrogens. We can look at hydrogens and think to ourselves, okay, there's going to be electrons associated with each of these hydrogens, and they will move from one compound to the next. Okay, but at other times during this particular chapter, hydrogens will be referred to as protons because they might be in solution, and when they're oftentimes in solution, they have lost their electrons somewhere. I don't really care where they've lost them, but when they're by themselves, they are considered protons. So we have to be careful what we're looking at when we refer to them either as an electron or a proton. But let's get into when we refer to them as electrons. Okay. So electron gain and loss can be determined by following the hydrogens, and so we're looking here at some compounds in which we see hydrogens bonded to other things, so we can kind of consider them as, neutral hydrogens. They still kind of have their electrons associated with them, okay? And so let's apply our definitions of oxidation and reduction to this very famous formula, right? We've got C6H12O6, that is glucose, okay? We most commonly use glucose because that's one of the most common compounds on the face of the planet because plants make it, okay? And so our bodies are good at breaking this apart, but they can also break things apart like fat and proteins as well, okay? But we're going to use this one because it's the most common one on the face of the planet. And what we want to do when we're tracking these high energy electrons is look at the hydrogens and figure out what's happening to them, okay? So let's look first at glucose, C6H12O6. We can look at that and say, okay, it's got like 12 electrons because it's got 12 hydrogens. And we want to see what does glucose become on the other side. And so to understand what it becomes, we kind of have to track the atoms, right? And okay, so we've got carbon is in glucose, we've got hydrogen, which is in glucose, we've also got oxygen, which is in glucose. Okay, so let's see what else on the other side also kind of has some of that stuff. Okay, and right away we go to CO2. Okay, CO2 has 6 carbons and it's got 12 oxygens. Those aren't the same numbers as over here, but it's got 2 of the same things. So chances are glucose, which we see here, probably somehow turned into the product of carbon dioxide. But we notice that it's obviously not the same. What has it lost? Well, it's lost those hydrogens, right? And so when we notice that a compound loses electrons, right, because it's lost these hydrogens, which I just told you we can consider to be called electrons, it's lost them, then that means glucose has become oxidized. And when it becomes oxidized, it turns into CO2. Okay, so follow the electrons. No, okay, so that's part of our problem. That's part of the redox reaction. We just saw in this oxidation reaction that glucose lost electrons. Well, where did they go? If something is lost in a redox reaction, something else has to gain the thing that was lost. Okay, if that makes sense. And in this case, we look to the other reactant. Okay, we look at oxygen. I'm going to see if we can track oxygen. Let's track it to since we already determined that CO2 was kind of a modified version of glucose, let's look at the other product here, which is water. Okay, that means that this oxygen, if we track it, okay, look, it looks like a oxygen here. There's 6 oxygen here. There's 12 oxygen. Okay, we can kind of go with that. But what has that oxygen gained between going from here the reactants to here the products? Well, it looks like it's gained those 12 hydrogens. Makes sense, right? Glucose lost those 12 hydrogens, also known as electrons, and it looks like oxygen picked them up along the way. Okay, and so oxygen has gained those 12 electrons. So if something has been gained, specifically electrons, gain of electrons is reduction. So this tells us that oxygen has been reduced. Oxygen has been reduced. It went from just being oxygen to gaining 12 electrons because it gained those 12 hydrogens, right? And so as a result, oxygen here on the reactant side has been reduced. It gained electrons as it transitioned over to the product side, okay? So by looking at this diagram, we can track the electrons by tracking the hydrogens, and we can tell what is being oxidized, which is glucose, and what is being reduced, which is oxygen, because one thing, glucose, loses those electrons, and the other thing, oxygen, gains those electrons. Okay, so again, just to review, what is being oxidized? Glucose, since it will lose those electrons, it will lose those 12 hydrogens, and then we can ask what does it become once it becomes oxidized? Glucose becomes carbon dioxide. Okay, what is being reduced? In other words, we want to know what is gaining those electrons. What is gaining those electrons that glucose lost? It is oxygen, since ultimately, I don't know why there's a question mark there, but oxygen is being reduced because it ultimately gains those hydrogens that glucose lost. And remember, I said those hydrogens can be referred to as electrons. So ultimately, oxygen gains those electrons that glucose lost. Okay? So what does reduced oxygen become? It becomes water, because it is oxygen that has gained hydrogens, okay, or gained electrons. All right, so how does this happen in our bodies? We want to know. The oxidation of glucose does not happen in one single step, as we saw in that previous graphic. Okay, so if we look at this, what I'm trying to get at is that indicated by this chemical reaction here, this indicates to us that glucose has these hydrogens, these electrons, and then all of a sudden it loses them and they go directly to oxygen, and in one step they transfer to oxygen and make water. Okay? Oxygen does not take the electrons directly from glucose. This actually does not happen. Okay? In between this side of the reaction and this side of the reaction, there are dozens of steps. Okay? So this is not a direct transfer of electrons from sugar to oxygen to make water. This does not happen in real life. And ask yourself, you might ask, well, why doesn't it happen? Why doesn't it happen like we see in the chemical formula in front of us? This is a very simplified version of it. It takes all of the detail out of it. It gives you the starting point and it gives you the ending point. It tells you that those electrons start in glucose and it tells you that they end in water. Okay? But it doesn't tell you everything that happens in between. If those electrons started in glucose and ended in water in one step, they just a direct transfer from glucose to oxygen to make water, it would be extremely explosive. Okay? And that's what this indicates right here. That's what this diagram indicates right here. A direct transfer of those electrons, those hydrogens, from glucose to the oxygens to make water gives you a very explosive reaction. And what actually occurs is a series of many transfers of these high energy electrons. These high energy electrons that start in glucose go through a series of many smaller reactions that harness little bits of that energy that those electrons tend to have and allows us to make little packets of energy that we can then use however our body needs. If we did not do that, the oxidation of glucose, if it occurred in one single step, it would blow up. Okay? It would be very explosive. And you wouldn't be able to actually harness energy. So much of that energy would just be lost as heat and light. And so one of the things I want to show you here, and this is something we unfortunately miss or lack from not being in person is the explosive, fun nature of some of these experiments that we could do, or demos that we could do. So I've got to show you this one. This is what happens when you put sugar and in a specific chemical, and you release all of those electrons at once, and they're accepted by oxygen all at once. This is what happens.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
Okay, so you saw it there. If we were to eat a gummy bear, could you imagine our bodies doing that reaction happening in our bodies? If we released all of the energy from those high energy electrons that was in the sugar of those gummy bears in one fell swoop in our stomachs, that is the worst case of gas anybody could ever have, to the point where your stomach melts and you die, right? It burns a hole right through your body. That reaction is so explosive and so intense in terms of heat and light released that if you don't use the proper kind of test tube to do that in, it will literally melt the glass and it will spill all that crap everywhere, okay? So it can be bad, and so that's exactly what would happen if our bodies did not release the energy of those electrons in glucose in small packets, in small steps. And so that's what we're going to talk about throughout this entire chapter, right? Is all of these small steps that release these little packets of energy along the way that are represented by the glucose. Now, to do that, we need something known as oxidizing agents, okay? Now, oxidizing agents are used in the stepwise oxidation of glucose, right? We don't want that oxidation done in one fell swoop, or our stomach explodes when we eat a bag of Skittles, okay? Or a bag of gummy bears or whatever. You turn into this fire everywhere, right? You belching out fire, crapping out fire, and you're just dead. So these oxidizing agents are vitally important to being able to transfer these high energy electrons from place to place in our cells, while all the time releasing little bits of energy along the way, okay? So oxidizing agents are the recipients of these high energy electrons. Therefore, they are the agents responsible for oxidation, okay? So a weird way to think about this is that oxidizing agents are being reduced because oxidizing agents are gaining these electrons, okay? So now this is something that I tend to try to simplify for you and try to understand what an oxidizing agent is. And so let me just pull up the definition of an agent here. I don't know if you can read this, but it says, this is from dictionary.com or whatever, a person or thing that takes an active role or produces a specified effect. Okay? So an oxidizing agent, in this case, is a thing or a molecule that is responsible for oxidizing something, for making something give up its electrons to it, okay? Another way I remember this is that I think of, I hear this term a lot. I don't know why I hear this term a lot, but I hear about it maybe in, I don't know why I hear this term, but agent of destruction or agent of death, okay? Maybe I watch too many like movies. Say this person's an agent of destruction. My kids are agents of destruction, agents of chaos. It's not like they're secret agents, but they are people who bring about destruction. They are people who bring about chaos in my household, right? So an oxidizing agent is a thing or a chemical that brings about oxidation in something else. It helps with oxidation in something else, if that makes sense. So as a result, if it's helping something else be oxidized, if it's helping something else lose electrons, the oxidizing agent will gain those electrons. It will be reduced. So the oxidizing agent that we just saw in that gummy bear experiment is a chemical known as potassium chlorate. It takes those electrons from the sugar and adds them to its structure in one fell swoop, and which is why it's very explosive. So there are other oxidizing agents used in cell respiration before the electrons will ultimately get to oxygen. So there's many different chemicals between glucose and oxygen that these electrons are transferred to before they ultimately get to oxygen. Eventually they'll make their way to oxygen in many, many steps, but they hit all these other kind of oxidizing agents in between. Okay? So if we look at this molecule, this is one of the oxidizing agents that we have to understand because it's a famous one. It's called NAD+. The oxidizing agent here is NAD+. If we look at this very complex molecule that we see over on the left, NAD+, the real part that we have to look at here is this, this portion of it. Okay? If we compare this portion of NAD+ with this portion, which is the product called NADH, we notice that it has gained a hydrogen, right? If we look right here, and we look right here, there is a hydrogen right here that was not here before, okay? And so what we see is that this NAD+ has gained an electron, so they call it NADH, okay? And so that means that this thing has been reduced. Gain of electrons is reduction, right? Or reduction is gain. Okay? This thing has gained an electron. So that means it's an oxidizing agent. It means that it helped something else become oxidized. It helped something else lose electrons. And it's helping our food. It's helping glucose lose those electrons. It will take those electrons. It will not do so in an explosive fashion, and it will give us this little NADH. So what we have to understand here is that NAD+ being turned into NADH acts as an electron transporter. NAD+ acts as an electron transporter. It shuttles our electrons around to these different reactions in a non-destructive way, effectively, right? It takes these high-energy electrons from glucose and it brings them to different parts of our cell, different parts of the mitochondria, and it will release that energy in a controlled fashion. So this oxidizing agent, NAD+, gaining an electron, a hydrogen, and turning into NADH is vitally important to our understanding of how cell respiration harnesses the energy that is found in glucose. Okay? So how is this energy transferred? It kind of goes back to chapter 8 a little bit. It's important to see that there is a change in the covalent status of these electrons as they go from different step to different step in respiration. We need to understand that they move from chemical reaction to chemical reaction to chemical reaction. So effectively we can kind of track these electrons through all of these different little chemical reactions that are found in cell respiration. Okay? And so this is what we would call a metabolic pathway. Specifically, it would be if you can remember, it's either a catabolic pathway or an anabolic pathway. This cell respiration would be a catabolic pathway because it links together dozens of different smaller chemical reactions to break down glucose in a controlled fashion. Okay? So those electrons begin their journey in an unstable configuration, which we would consider to be glucose. And they end in a more stable molecule, and as they do this, they release free energy as they go. So this goes back to some of the stuff we talked about in chapter 8. As we take these electrons from something like glucose and we put them through all these little teeny tiny chemical reactions, during this process they release free energy along the way. And that's where we're going to talk about all these gritty details. We have to remember to track these electrons. This entire process is all about tracking where the electrons started. They start in glucose, and then where they end up. They end up here in the electron transport chain. So we got to understand where they started and where they're going. So as we start our journey our detailed journey into cell respiration. I will cover each one of these different phases in its own specific video. We're going to cover glycolysis in its own video, talk about the Krebs cycle in its own video, and then the electron transport chain and oxidative phosphorylation in its own video. And eventually we will get to this grand finale where we finally figure out how we had started with a glucose molecule and we end up with ATP, which we all know happens, right? We always refer to these glucose molecules being able to be broken up into like 36 to 38 ATP. This is the process in which it happens, okay? And we're going to talk about all the little gritty details along the way, and I hope you enjoy the ride, because I always do. This is one of the hardest chapters to teach and learn, but it's also one of my most favorite ones, because when you understand it, it is relatively mind-blowing, and I only understand it to a just under the surface level. So I hope you guys can enjoy it and appreciate it as much as I do. Chances are you might not until you study it for a couple years, but try to and get as much out of it as you possibly can. All right, so I'll be back with a couple more videos, and I'll see you later.